Good evening. Could you please give me green? Could you please give me a check if you can hear me? Thank you. Then check, that will be great. Great. Thank you guys for coming today. I know it's we were scheduled to have a break this time, but by taking this class today, we will be on track. So we would have made up all the classes that we missed. So last week, I don't know if you remember, but last week we talked about series circuits. In particular, we talked about three things about series circuits. If you guys remember, we talked about how to put series circuits, to put resistors in series circuits, and then we talked about how to put power sources in series circuits, as in we talked about motors and transformers, the coils, how to put the coils, motors, and the transformers in series circuits. So we talked about three things about series circuits. And my friends, what we're going to be doing tonight, we're going to be talking about the same three things in a parallel circuit. So we'll talk about how to put resistors in a parallel circuit, how to put sources in a parallel circuit like generators, batteries, and so forth. And we'll talk about coils, how to put coils together to make a transformer and a motor, three and single phase. So really interesting. I hope so. So that's basically what we're going to be talking, guys, about today. Eric, my friend, if I can have your attention, we're going to start with the parallel circuit. But before anything else, if you guys remember, we always go and review what we have done. Let me ask you, has any particular question about the quiz? Any question that you want to discuss in particular? I always go over the quiz. Unfortunately, I'm looking at my email here right in front of me. I have not received your results yet. So big deal, but I assume you guys did good in it. No news is good news. So Byron, my friend, anything in particular you want me to go over? Any quiz? I see a chat here. Question number 14. Okay, we'll highlight question number 14 in particular. We'll go over all of them, guys. Question number 14. Great. Okay, let's go ahead and start. We have a good in front of us. So first, we always review, guys, the quiz of the night before, which is series circuits. A couple of things here. Number one, usually talk fast, Eric. So feel free to stop, friends. Series circuit has individual resistor. Again, we're talking about series circuit. It has 2, 3, 4 resistors connect across a voltage of 120. The total resistor of circuit is. So if you put them all in series, as we guys remember, all of them in series, and you put them across a 120 voltage, and they are asking you about the total resistor. So as you add them all together, so when you add them all together, you end up with 500. Straightforward. Find the total resistor. One rules of series circuits is the resistors add up together, with a disaster from a power point of view. Okay, when a voltage of 240, remember it's a voltage 240, is applied to a series circuit, a total resistor of this amount, 3 resistors. Now we have 3 resistors, or 4 resistors. 3 are 1 and a 2 and a 3. So 3 value of the 4th resistor, and we need to find the value of the 4th resistor. That could be, guys, tricky a little bit. So we have one resistor, we have the other resistor, the 4th resistor, the 3rd resistor, and the 4th resistor, and let's draw that one, and they are sitting across 240 volts. Okay, one of them is 100, and the other is 150, and 120. So 100, 150, 120, and the total resistor, the resistor that can represent all of them, that total resistor, right, is total resistor, total is given as you see, 300. So this is really, and this one is R4. I have no idea what R4. So if you guys, if I were you, here's what I start? I start by drawing the circuit like this. And guys, remember, those of the series circuit resistors add each other's up. So that would be a piece of cake. That'll be 100 plus 150 plus 120 R4, because I don't know what R4 is. Everything, guys, is equal. Everything equal 380. And friend, I'm not going to go over this one. You guys know how to add all these together. So the next step is you add all these together. So they give you 250, 300, 370, and subtract from 380, and guess what your answer would be? Your answer would be 10. Any question about this one? Any question? So the key is, friends and everybody else, the key point is to know how to write the equation. So this is what we call a single unknown equation, right? Everything is known except that one from algebra. And add the 100, 150, 120, add them up, subtract them from 380, and got yourself a 10. Questions? Why? Any questions? Any? I assume if you don't have any questions, we'll move to the second one. A series circuit containing 5 resistors connected across 120. The voltage drop across each of the four resistors is this 1, 2, 3, 4, and the drop of the fifth resistor. This is the same thing. In a series circuit, guys, the voltage adds up. So if you're going to start, you start with 120, the total voltage. That should equal a 22 plus a 28 plus 25 plus 10. And guess what? The fifth resistor, I have no idea. So I'm going to call it V or E, V5. So my friend, from all what you have to do right now is just add these up, right? And subtract them from the 120. And based on this one, your answer should be, which is 10. Also, any questions? Make sure I'm not going too fast, Matthew, my friend. Any questions? Okay, moving to the second one. Circuit has 3 resistors connected in series. There's 3 of them. They're connected in series. R2 has a resistor of this amount. All the voltage across R2 is this. R3 has a voltage of this. The circuit that to R3 is. This is a tricky one. So if you guys look at it, first, always draw the circuit, because that's a piece of equipment that you would never forget. And I have R3 here, and R2. I have R2. Here's my R2. And I know that R2 is 200, is given to me, R2. And the voltage, 200 has a 200, and a voltage across that resistor of 50. Of 100, a voltage drop of 100, okay? And what is the current across R3? Across R3. Well, who cares? I mean, as you guys know, the current in the circuit is still the same. The current here equal to the current here equal to the current here equal to the current in a series circuit. So current across R2, it's the same across R3. So piece of cake, Chad. You take the 50 volts and divide by 200, and it's 50 volts divided by 200. You're going to get yourself into A again, which is 0.25. This could be tricky. Any question guys about this? You have to the current through a series circuit stays constant. Through a series circuit stays constant. And guys, the I2, this is I2, right? This is I2. I2 is the voltage V2 over R2. As because this is a series circuit, I know that I3, as a matter of fact, equal I2. So piece of cake. Question? No problem. Again, questions, guys? Any questions? Tricky one, so you have to pay attention to it. Circuit has 4 resistors connected in series. There's 4 of them. They're connected in series. One has this amount. The voltage drop is R2 has a 200, and the voltage drop as so has a 4 resistors connected in series. Resistor R1 has a resistance of this amount and a voltage of this amount. Okay, so this is really very similar to one that we just guys finished. So here's what I know. I know that R1, which is here, R1 equals, that's all what I know. The voltage across R1 is given as 50 volts. That's what you know. Let's see, what is it, R2? Let's say this is R2. Here's R2. R2 is 200. R2 is actually 200. Okay? If here's the key point, and they're asking me about a voltage across it, as in across R2. So what they want to know, guys, is they want to know the voltage from here to here. That's 2 or 2. The thing I have to understand is, first, if I find the current here, guys, and the current here, and I divide the current, I multiply the current by the resistor, I find the voltage. So that's, Jacob, that's where you start. You start by asking yourself, if I find the current in a series circuit stays the same, so then R1 is the same as R2. So long story short, you're going to find, the first step is to find I, in this case I1, which is 50 divided by 100, and then take the 0.5 because it's the same, and you multiply it, my friends, by 100, and 5C. That will give you C. You multiply the 0.5 by 200, and that will get you what? Get you R. Question, guys, about this? I want to make sure, Matthew, my friend, Dan, Eric, that you guys know how to do that. It should be second nature for all you guys have to know how to know this stuff. This will be on your journeyman and master exam. No question asked. So I'm going to emphasize it tonight, guys. If you have two things, there are 4 things for every resistor. If you know 2 of them, you can find the other 2. If you know the series circuit rules, you can predict and find the rest of the Okay, move not too much because I have to keep going into the parallel, guys. Circuit has 4 resistors, again 4 resistors in series. The voltage drop across resistor. Each resistor is 120 volts. The supply to the circuit is so 4 resistors. If you remember, each one of them is 120. So what would that give you? I will tell you if all of them are the same. So R, and this is R, and this is R, and this is R. So if the voltage across them is the same, then they must be the same value. And each one of them is 120, guys. So the voltage drop across each resistor is 120. The voltage applied to the circuit is, so basically you take 120 plus 120 plus 120, and that will get you D. That will get you D. Add the voltage. So 40, that will get you the 480, right? And all you have to do is just add the 120, the 120, the 120, and the 120. Because voltage in a series circuit adds up. Okay. Moving to 7. The voltage of 120 is applied to a circuit with 4 resistors. Again, 4 resistors. Drop across 3 resistors is this amount, 1, 2, 3. The across the 4th resistor is piece of cake. If the voltage adds each other up, here's the total voltage must equal 30 plus 20, 10 plus the unknown, which is a E or V, E, what we say E for. And then I'm not going to tell you, guys, from the math. If you don't know how to solve this one, you really need to work on your math, guys. 30 plus 20, 50, 60 divided by 120, so the answer should be 7 is C. So that's basically how we start. Any questions? Any questions? Any series circuit rules, which is the voltage adds up to the source voltage. Adds up to the source voltage. Series consists of 4 resistors with values. If the voltage are applied to the circuit, the current flows in the circuit is. That's very easy, guys. I have 4 resistors in series sharing a voltage. So if I want to find the current from the 4 resistors, right away I find the V total. You guys remember the V total over the R total? And it's adding all these together, which is which is the 160 plus the 100 plus 60 plus 80, and each other. And when you do this, A should be should be 5. So dividing the voltage by the total resistor. Consists of 4 resistors with resistance values of the following. 60 volts applied to the circuit. The voltage drop across the resistor of 100 is. So this is 2 steps, guys. First, you need to I total. Well, the first step is to find R total. I'm adding these babies together, which looks like 200 R total. To add them all together, that will give me 2,500. If I add them up, 1,000 plus 1,000 plus 500, that's 500. That's step number 1. Step 2, guys, is we need to find the current. So total equals 50 divided by 250. This step number is 2,500. And step number 3 is to multiply the current. The current one, I total, which is that current, multiply it by 500, because the voltage across the resistor 500. 9 is C. In my case, 9 is C. Okay. Question, guys? Any question? And I hope I'm not going too fast. Then, my friend Matthew, any questions? Basically, I assume I'm going fast, but please stop me anytime. I hope I'm not having that you know really good. Circuit in question of 9, the voltage drop across the 1,000 resistor will be the same thing, guys. The 1,000, you take I and you multiply pound and you multiply it by the 1,000, and should be C. My answer should be C. One more time. Any question guys about these calculations? It should be to all of you guys. No. The rest of them are not calculations, just multiple choices. Start with 1 is the force that pushes the electrons through the resistor. As we all know, this is D, right? D. Voltage is the force that pushes the electrons. In a series circuit, the total voltage applied to the circuit equals C, the sum of across each resistor. No one path for current to flow in a series circuit, right? This is 13 is D. Now 14. In a circuit, the flow of the current is, now 14, our answer is right here, inversely proportional to the sum of all the resistors in the circuit. Largest resistor in the circuit. I want to discuss it. In a series circuit, here's a series circuit. Let me just quick because you guys some of you want to know that one. The current. So we're talking about the I, the current in the series circuit right here. I, the current in the series circuit, okay, is inversely proportional to the sum of all the resistors. It's proportional, guys. Here's what it means. If the resistor, the total resistor, if R total goes up, if R goes down, so it goes up, the other one goes down. One goes up, the other one goes down. That's called inversely proportional. Directly proportional, Byron, my friend, directly proportional, they both go up at and down at the same time. Down at the same time. That's directly proportional. Inversely proportional, if one goes up, the other one will go down. Okay, so that's basically the answer. Why do I know this? How do I know this? If you guys remember from Ohm law, let me just write Ohm's law for you. V or E equal I times R. Okay? Now, here is constant. If the voltage, let me tell you, the voltage here stays constant. Okay? The voltage across the voltage. So if the current here goes up, then down. And why is correct? Because they have to equal always to the same amount of voltage. What We'll explain it, and that's why A is the answer. Okay. It is true that 15 is A, as the current is greatest at the beginning of the series circuit. The current is the same at the of the series circuit. The current is the same. It is the same. Are normally wired in series, right? 16 is series B, and I'm going to pass a little bit here. When the source voltage and the source of resistor are known, the voltage drop across each element of the voltage divider can be computed by using the, you guys remember the greater voltage, the general voltage divider, special voltage multiplier. So our answer for 17, which is the voltage, the key point is the voltage divider formula. Moving to the chassis ground. Chassis ground, guys, as I told you, they use it in the automobile industry, airplanes, ships. They use the frame, the body or the frame. Just, I see your hand is up. I'm going to go unmute you. Go ahead, Gerald. Hear me? Saying, want to check in? Okay, thank you. The chassis, guys, as I said, chassis ground is not like the power ground. Chassis ground is D, which is all of the above. The common connection for parts of the circuit. So I don't really want to. If automobile, guys, and you bring your circuit, you bring your voltage, what's your negative right here to the frame, and your positive directly to the light, and so forth. And there's another circuit, another light here. You feed it from here and you tie it to the ground, and so forth. So that frame, the frame is usually the reference point. For other parts of the circuit is normally driven into the ground. Yes, is not normally driven into the ground. Is not, which is true. You can't car to the ground, can you? You can't drive it to the ground, but you can bond it and ground it. Unless it's your teenage daughter or son, then you can ground it. May be presented by either the chassis ground symbol or the air ground symbol. So the key, again, we really don't the automobiles, but that's where you can use the frame of the airplane, the frame of the ship, or the frame of wires. But your reference point, even if you use wires to bring the circuit back here, you set it to the frame of the vehicle. Okay, power used in a circuit is equal to 19 is A, is to the sum of the power in the whole circuit. All parts. A voltage divider works on the principle that number 20 is D. Divider works on the principle. What principle works, Jesse, my friend? The voltage divider works on the principle like if the current is the fattest, fluffiest resistor hugs the most amount of voltage. That's really the principle. The voltage across any resistor in the circuit is proportional to its resistance. Across any resistor in the circuit is proportional to its resistor. If it could be if it says directly proportional. If the reason why this is not right is because it's proportional, directly proportional. The average drop across a series circuit must equal the average applied voltage. No, the current through any one resistor is proportional to its resistance. Proportional to no, so that's wrong. So the principle that it works on as a Brenner, my friend, is the largest, biggest resistor will consume the most amount of voltage. So that's basically the principle. Okay, one more time. And the parallel circuit. We start our discussion of the parallel circuit. We're at the quiz, where everybody wants to take the quiz. Green check, yes. Able to take the quiz on time because most of you take the quiz. About the parallel circuit. Now, my friend, you and I know are the single most important circuit in the universe is the parallel circuit. Because circuit, you can plug your microwave, you can plug your lights, chat talking to you guys via the The because of the parallel circuit, my computers around me are plugged in parallel with the source. The smarter than Chad Brenner decided in the universe, the electrical universe, the way to stabilize by making the voltage constant and current varies. And that's basically voltage constant. If you remember, the voltage stays constant for the most part, and what varies in your house and mine and in any building is the current. So for example, if here's my panel here, and that's basically the concept of parallel circuit. I have a 200 amp panel right in here, and I tie equipment to it. I'm going to tie my chill here, or my AC system here to this panel. I'm going to take a feeder from this panel. I'm going to go tie some pump, and of course, all these, I'm going to go come over here and put my lights over here for circuit. So one thing common, guys, in the whole circuit, this is single phase. This circuit, this voltage is 240 volts, and 20 obviously wants to ground. The only thing common between these loads are either they're 120 or 240. So it is the current. I turn my AC on, the current in the circuit goes up. If I turn it off, the current goes down, and so forth. The voltage stays, for the most part, Byron, stays constant. Very, very important concept in the parallel circuit. Very important. Okay, the characteristics of the parallel circuit, the rules, the 4 rules, as a matter of fact, for the and quantities, voltage divider, the same guys that we did in the series circuit, we're going to do it in the parallel circuit. And how to calculate current through the voltage divider formula, and Mr. Kirchhoff's law, which adds up in a parallel circuit, and the voltage adds up in a series circuit. Before we go ahead, guys, like I did last time, I have to take a second here and write the rules of the parallel circuit. And I can write here, and if you summarize them with just a few, rule number 1. In a parallel circuit, guys, I think I have one here. In a parallel circuit, you have more than one path. Can you guys see that there's more than one path for the current to go through? Can you guys see how there's no more than one path for the current to go through? So rule one in the parallel circuit, more one path. Interesting. So that's rule number 1. If it's a parallel circuit, it has more than one path. Rule number 2. Rule number 2 in the parallel circuit, guys, and keep doing it. Rule number, voltage stays constant. You guys remember the V total? The V equal V1 equal V2 equal V3. What means V3? What that means is the voltage inside your panel at home stays 240/120, and the load comes up when your microwave kicks in, when air conditioning kicks in, the current goes up, but the voltage, for the most part, constant. The voltage stays constant. That's how 99.9% of the power industry works, and thank God for that, because if you buy an equipment, guys, that run at 120 and voltage goes every time a load comes in, like in a series circuit, the voltage drops to 60 volts in every single piece of equipment, if you're lucky. And if you're not lucky, you're going to burn the house that houses this equipment. So that's what makes this rule here makes the series circuit, parallel circuit, superior from a power point of view. Rule number 3, guys, the current. If you guys remember microwave, here's my total current. My total current equals current that goes through my microwave plus the current that's going through my TV plus the current that's going through my air conditioning. That goes through every single piece of equipment, every branch. We call it circuits, right? Branch in my equipment equal the total current that's coming out of my panel. Very interesting. Meaning the more you connect, Eric, my friend, the more current you have. But stays, for the most part, stays constant. So number 4, don't go down then without knowing these rules. Rule number 4 is power, guys. The power P total the power of my 24120 panel, the power that's consumed by my microwave, plus the power that's consumed by plasma TV, plus the power that's consumed by my sump pump in this case. So 1, 2, 3. You keep adding, Jacob, my friend. You add the power consumed by your refrigerator and every other load inside your building. Questions. These are the most important rules for parallel circuits. Any questions about these? You count, my friend, without understanding these fully. Any questions? Any questions? So go to your journeyman exam. Make sure you know these rules. You know, a couple of questions, 1, 2, maybe 3 questions about parallel circuit. The most important rules of a parallel circuit. The most important rules of a parallel circuit. I'm attention, guys. We'll talk about this one. What I'm going to be talking tonight, I'm going to summarize it with the following. First about the resistors, which is resistors. How am I going to resistors? Put them in a parallel circuit. The second thing I'm going to talk about, guys, is generators, power sources. How do you put generators in parallel? And the thing I'm going to talk about motors, called coils, guys. Motors. How do we put motors in parallel to make different voltages? And one is a transformers. XFR is my transformers. So these topics that we touch on in terms of applying a parallel circuit. Anybody has any questions? Circuit, the most important circuit, as I said, in your job and I, being electricians, these are basically 99% of what we do. We hook up in parallel. We'll remember them. Rules. One path, we talked about this one, guys. Current is additive. It adds up. Here's an example, guys. I want to bring to your attention a few things. I'm going to take my current here and make it, look at the, guys, regardless of it's coming positive to negative, negative to positive. Here they're showing it you see the current? The current is N. Now this is a moment of truth right at this point. Some of it will go here and some of it will continue over here. The third, moment of truth. Some of the current is going to go over here. So can you guys see how the current is splitting? At this point, if you guys can follow me, at this point they're going to add up again. See how it adds up again here? Oops, right, coming from here, it's going to add up again to be the same. To be the same. Very interesting concept. So if you guys look at the 3 amps, let me just have done. I entered here with 3 amps. 1 amp went through here. 2 amps continued. 1 amp went here. Another amp went through the other one. So what do you guys think the current right here, where I pointed? What do you guys think? Can anybody tell me what the current should be here? Can you see that one with Chad? What would the current be right here? What would I say, Chad? Can you guys see that? Can you change, or on my screen here? Can you draw on my screen? Do something. Can you current right there where I pointed? Yep, I see a right answer here in chat. Right where it says my bad 30 here. Anybody? Okay, now that the current here is 2, you have to review your rules of parallel circuits. Unreal. So let me say one more time here. Thank you. How about the current right in here, guys? I'm going to move Chad again to this side. What do you guys think the current right at this point should be? The current point where I have my name. Well, what do you think the current should be? 3. Thank you. Here should be 3. So the current is up. The current adds up. Splits and adds up. That's the circuit. Okay. On all voltage. Voltage, as we said, guys, the single most important thing about the voltage stays constant. Let's go to my beautiful drawing here. If the voltage source right here from here to here, let's say this is a 24 volt DC. right here, right across these two is 24. Right here, if the voltage should be 24, and the voltage right across these, it should be also 24. They stay the same. That's my TV. That's my refrigerator, microwave. The voltage is the same. Otherwise, you burn equipment in a parallel circuit. Voltage drop across any branch in parallel is the same as the applied voltage. Is the same as applied voltage. Now, it's cool about the parallel circuit, except one rule I forgot to write it for you guys. With total resistor. The total resistor in the parallel circuit is looking very important in terms of concept. Ugly looking, but very important in terms of concept. So I'm going to go to another rule, and I'm going to, this rule number 5. Rule number 5, I'm going to write it right here if you guys want to write it. It's resistor. The total resistor, guys, here's how I write it. 1 over the reciprocal, they call it the reciprocal. 1 over the total resistor is 1 over R1, 1 over R2. Total resistor. And we talked about total resistor. Total resistor, if you have 2 of them, you can put them, open the door, throw them in the garbage, and buy yourself a resistor that can do the function of these 2. For example, a microwave and a refrigerator. Unplug your microwave and your refrigerator, throw them in the garbage, buy yourself one piece of machine that can have a microwave and refrigerator all in one. That's really of the total resistor is. The total resistor is. So take your house and your house, get rid of your house, get rid of your house. That's resistor 1, resistor 2. So a big house where you and your neighbor can live in the same house. So that resistor of your house seen by the resistor of your neighbor's house seen by the grid. Get rid of them and put a big panel that can feed both of them. That will be the total resistor. If that. Okay, basically the rule number 5, the resistor is a reciprocal. And you guys, if you haven't heard that term, reciprocal, reciprocal of a number is 1 or that number. So a reciprocal of a 5 is a 5th. A reciprocal of a 10 is at 1/10. A reciprocal of 100 is 1/100, and so forth. So a reciprocal of a number, if the number is say 10 and you need to find the reciprocal of the 10, you take 1 over 10. Connected in parallel, the circuit is decreased. Now, one of the most fundamental important rule in the parallel circuit. Every time you guys add the load to the grid, the overall resistance of the grid goes down. That's beautiful. So I have my house here, and I have neighbor's house here, and right in between, they decided to build another house right in here, and all are fed from a thread coming to each one of these homes and continue. Now, every time, and if you're looking at it from this point of view, this is my R total. When you add a load, the R total goes down. Because of this concept, my friend, and you can bring the power, the backyard power plant here, all the way to the cities. That's because every time you add a load to the grid, the overall impedance of the grid goes down. Well, there's other rules. I'm just trying to minimize it, but at least doesn't go up. It doesn't go up substantially. Put it this way. Unlike the series circuit, every time the resistance goes up and up and up. Time you add more homes to the grid, you need a conductor the width of Interstate 94 to bring the power from there all the way to Minneapolis. If you are to bring it in a series circuit, just to give you how big of a problem is that. You need a conductor the width of 94 to bring the power from the power plant in Becker all the way from Minneapolis. If you are to use a series circuit to feed all these homes, if you can even. So resistive elements are connected in parallel. The circuit resistance is decreased. Very good. I want to bring to your attention, look at this. This is a 15, this is a 10, and this is a 30. When I connect them in parallel, look at what the total resistor is. The total resistor in a parallel circuit is lower than the lowest resistance in the circuit. So the 5 is lower than 15, also lower than 10, and it's also 30. So it's lower than the lowest. What's the lowest in this circuit? The whole thing, the lowest resistor is here. So 5 is lower than the lowest. Here's an example, Joe, for example. If I told you, here's a multiple choice. I told you RT, just what that RT equal from RT. Option number 1 would be 10. Option 2 would be 12. Option number 3 would be 11. And option number 4 would be 5. So just by looking at them, I can't use 10 because the resistor have to be lower than the lowest. I can't the same concept. I can't use 11. By default, without the calculation, this should be the answer. Gerald, my friend, let me go and mic you. Gerald, can you hear me?
Your audio keeps fading in and out on me. On a wireless network in the motel.
I'm sorry. Can the rest of you guys hear me? I'm just trying to see if it's issues. Can you hear me clear? Can you green check if you can hear me clear and loud? Can you? Okay. Yeah. Okay. It's the audio. It seems everybody can hear me here, though. Keyboard side. Thank you. Basically, what's the elimination? It's lower than the lowest. Lower. So remember, lower. The lowest. Okay. All right. So is the I'm trying to I have my order. Okay. Ask you one more time, guys. Can you hear me? Can everybody hear me clear? Can everybody hear? Can you hear me? Seems Joey can't. Okay. All right. Okay, that's good. Really, the very interesting rule. So we know the rules, guys, of the formula. Resistor of each value, parallel resistors, product. Now, to find resistor of the series circuit, there's a few rules that they allow us, guys. Number 1 is the product over sum, reciprocal formula, and divider. And resistor of equal values. A couple rules. Take these with you guys. If all the resistors are the same, the total resistor is 1 divided by the. If you have 100 resistors, each is 100 ohm, 100 ohm, and they are all put in parallel. All of them are connected in parallel. All these 100 are tied together in parallel. What's our total? What's the R total? The R is a piece of cake. You take the 200 and divide it by how many of them you have? 100, and get you a piece of cake. Get you 2. That will get you a 2. I don't divide the number 100 and get you 2. That will be 2. Okay. Very interesting. That's kind of a shortcut, a special if all are the same. The special rule. Any question about the special rule? Special rule. Make sure you know how to use it. Very easy. Product over the sum. The product of the sum is simple. It says, hey, by the way, if you have two resistors and you can take two resistors at a time, and that one resistor that can replace them, red is the one that's going to replace them. This is microwave. This is my fridge. Okay. And this is R1 and this is 2. And you need to cut the circuit right in here, get rid of them, and buy a microwave fridge. That's what basically a total resistor is, microwave fridge. What resistance do I need for this microwave fridge? The product, you can take the multiply each other, the product, that's where the name is, the product, all right, let me say that, the product over the sum, okay? The product over the sum. So you take product and you divide it by the sum, the product over the sum. Example, if it was 10 guys and this was 20, and you take 10 multiply 20, the product over the sum is 10 plus 20. So take your math, this is a 200, 30. So if you take 0, so 20 divided by 3, that will get you close to say 7. I'm just approximately 7. 7 by 3, that will get you close to 7. About the product over the sum rule. The product over the sum rule. Any about the product over the sum rule. Make sure that you know how to use the product over the sum rule. Microwave refrigerator specially designed for you. You can use your microwave and fridge and install that piece of equipment that function as a microwave fridge. Guys, to get you to understand what the concept of total resistor is. That's basically, or so remember the first rule, guys, they're all the same. This rule applies if you have two, taking two at a time. And if you have 100 of them, you take 2 at a time. Then take that total with another. Here's another 2, one. The same thing. The total with the second one, and you keep analyzing the circuit. To a reciprocal. The reciprocal, as we said, guys, is 1 over the number. So here's an x. A reciprocal x is 1 over x. As in the power industry, the reciprocal is called conductance. So let's take these R. You take 1 over R on the resistance of the flow of current. 1 R is the conductance of the flow of current. What does it mean? Means 1 over R measure how easy the current can go through the conductor. And two of you guys ever probably will deal with conductance. Conductance is big deal when we deal with power system analysis, guys. Big deal. In 2 courses in college, studying that sucker, the conductance agents and conductance. So it's that you say 1 over R, it's called conductance. That's what is of the current can go through the conductor. So the reciprocal method, guys, says 1 over R total equals over R1 plus 1 over R2. Okay, then 1 over and do the calculation, or you can use this formula, which is R total equal 1 over, and I can't cite the word, 1 over 1 of them. 1 over each one of them. Let's take an example. Let's say 1 over each one of them. Say the first one is 1 over 10 plus 30 plus 40. 10, 20, 30, 40 resistors in parallel, and the total resistor, R total, that's how you find them. The scientific calculators, guys, allow you to do that one right away, 1 over, and you do the calculation. I have a non-scientific calculator, like the one that they use the exam, and to 1 over each one of them, and then take 1 over the answer. So you can see it's a little bit involved. I teach the exam prep. I tell the students, use these and put them in the memory, guys. Take 1 over R1, put it in the memory, plus 1 over 2, memory, plus 1 over 3, plus memory, plus memory. When you're done, hit equal, and then 1 over the end, and that should give you our total. You have to practice it a couple of times to make sure that works. Practice it times to make sure it works. Okay, that's about this formula. Any question about this formula? You might take a couple of examples to take in how to put a resistor. How to put a resistor. Okay, at a point where we can break, let me take a quick break and then we'll do a couple of examples. Let's see, what time is it here? 50. Let's give you guys, let's 7. Let's, okay, 7:30. Let's 7, let's say 6, 50, 58. Let's give you 6:58. Okay? So let's get back to 58 and then we'll take a couple of examples here. check in, please. If you, my friends, understand the parallel circuit area and then, my friend, and Brad, we're going to go over a few examples in Delmar. Example number 1, number 2, and number 3, and I'm going to go over them with fast. Stop me when you feel I'm going too fast. I got our textbook of electricity. If you have third edition, 171, and I don't know if you guys have second page 151. So yes, my friends, I leave my desktop with you. So I'm going to go to desktop and adjust a few things here. So share desktop monitor 2, and my stuff over here, and you guys can get me a few things. There you go. So from there, let me grab you and move you in here so I can see you. Okay, you can see the feedback. Just so I can feedback. Make sure you guys know how to adjust your schedule so you can see the feedback. Right. And I can even go as far as that one. Put this and see that. Let me see. I go as far as getting, so let's split the videos too. Oh, okay. All right. If you with the parallel with the circuit, you've seen that one. Example of parallel circuit. Before you get that one, guys, I want to bring to your attention very interesting. If last week we talked about every single component in a series circuit has 4 things that we need to find. So if you guys look at this here, it has 3 things plus the power, and here it has 3 things plus the power. You can get the power, and so each one of these branches has 3 things plus the power. Things that you can find or given plus the power. Very important. Series or parallel circuits, you can find, so you have the voltage, you have the current, and you have the resistor plus the power. Current, resistor, power. Voltage, resistor, power. Very important things to understand about any circuit, guys. That's how make sure that you know in one. Let me see. Okay, there you go. All right. There you go. So let me get that one here. Okay, moving on to the second one. Here's R. You're familiar with loads resistor from the panel all the way into that exact paralleling means in terms of power circuit, and we're going to go, my friends, into the rectangle. Okay, here's the example, guys, that we have. Really interesting one. I will bring to your attention, my friend, that the example that we do is what we're in and what we need to find. We are given, I will bring to your attention, guys, what's given. We're given the resistor, the resistor, the resistor, and the current. So the total current and the resistor of every branch, and we need to find the voltage, the current of every branch, including the total power coming to the source. Very interesting. We all voltage stays the same. The only way to solve this problem, guys, is by finding the total resistor. The total resistor. So I'm going to go find the total resistor R, because it's not total, equals 1 over, and that would be 1 over, I'm going to write it right away, 1 over 300 over 200 plus over 600. my friends, where did they get your, there you go, let's get videos again. Let them, if friends have, if you have, parallel, if you have a calculator, a scientific calculator like this, Casio or Texas or any one of these, it's so easy to do this one. You're going to go, in my calculator, I can use, I can use 300, shift, x, 100, shift, 1 over x, plus 600, shift, 1 over x, equal, shift over the answer. And my guys will be 100. Very easy if you have a scientific calculator like this. Very easy. The good, Joanne, friend, is they don't allow you to have this calculator in the exam, the Germany, to put the stuff in the memory. So keep this in mind, guys. So this one, we find it. This is 100 ohm. This is 100 ohm. Now, which one? This is our total, which is right in there. This will be 100 ohm. 100 ohm. About you guys, but if I have the voltage, if let's just give you ET. E total from ohm equal I total multiplied R total. R total. So for this one, I found a 0.6 by 100 and get you 60, right? That'll give you 60. So the voltage here actually equals 60 volts. Percentage, that's 60 volts. And I'm going to find the power, guys. P total, E total. I have the 60, the voltage multiplied by the current, which is 0.6. And you go 0.6 times 60, and up you go with 36. So my 6 watts. So my power is 36 watts. What did I do? I found the voltage. I found myself the voltage here. Let me grab if I can get a different calculator. I found voltage. Current is given. I find the resistor. I found the power. So I found everything I need about one branch, which is the source. Can you guys see that? I found everything that I need about the source. The source from the resistor, the total resistor, the power, the voltage, and the current. And there's about R total, P total, and E total. How about the next? If you guys don't have any questions, any response here? Everybody knows how to find the response right at the bottom. So that's for branch number 1, guys, which is piece of cake. But friend, your camera is not on. I'm looking at your cameras here. Okay. If you guys look at branch, I'm going to do branch number 2 now, which is right in here. This is the branch I'm going to be working on. I don't know, friend Joanne, if you look at the voltage, V and V and V stays the same, right? All these 3 V's, because it's a circuit, these are actually 60 volts, all of them. Or what did we find? Yeah, we found the 60 volts. Each one of them is 60 volts. So there, from finding the voltage, because the voltage across parallel circuits is the same. From the voltage and the resistor, I can the current. So I'm going to do one of them, one current. I'm going to take I, for example, I1 equal 60 and by 300. 60 divided. Have your calculator, 60 by 300, and that will get you 0.2. That will show 0.2. So the current, I know the voltage. If the power, guys, is piece of cake. If you want to find the power, that might not be the right color. I don't know about you if you can see it. I want to find the power, which is P. Let's say P1, for example. P1 equal. I found 0.2. In our, and the voltage is 60. So here's 2 times 60 and got 12 watts. So the answer here is actually 12 watts. About how to find the voltage and the current. Any questions? Any the voltage for branch 1. Everybody guys can see that the voltage stays constant, and voltage and the resistor can find the current. Everybody can, Joanne, Gerald, maybe you can see the interface, Matthew, and question. Very interesting to know. This could be easy German exam, very easy to find. It's better to give you the voltage, very easy to find it. Okay, how you start. And I don't have room in the screen, so I'm going to go take a snapshot of my screen and get of my screen. There you go. I want to show, if you guys look what they did, here's voltage that we said. First we found the R12, then the voltage, and then from the voltage we current, which is okay, finding the current. And I really want to do one example about the current here. Take the current here. Okay. Okay, so I want to find the current 2, guys. If you look at I2, very easy. Since I know 2, I equal E2 divided 2, and that's piece of cake. You have 60 by 200. That will get you a 0.3. The same token is now I need to find P2, P.3, which is the current, and multiplied by the voltage, which is 60, and you take 0.3 times 60, and you get yourself 18 watts. You get 18 watts. If I3, guys, I take the same thing. I3 here equals 60, and if you get you a 0.1 amp, I will find the power P3, piece of cake, Chad. It's a P1, I1, or the 0.1 amp, which is a 3 multiplied by 60 and 6 watts. Anybody any question about how to analyze this circuit? Analyze this circuit. The more is to find how to start by finding this branch. And the key point, that little chain is R total. If I find the R total and then the V total or E total, then all E's are gone. Then from E's and the R's, all the R's are gone. And then from the E and I's, I can find the P's. Right? Take a baby to enter and to the next slide. Okay, bring to attention. Can you guys see now? This is where I want to a few things here for this circuit. One to understand is if you guys look at the total resistor, voltage stays the same. Voltage as series circuit stays the same. The thing you have to know is that it adds up. Can you guys see the current here? Add to the current here, and here, here. Can you guys see that? If you add the current, 0.6 equals 0.2 plus 0.3 plus 0.1. Very good. So that's a parallel circuit. The third one is the resistor. The total resistor is the reciprocal of all the other resistors. Can you guys see the total resistor? That's the reciprocal. And the last thing to mention is the power. If you guys see the power, it adds up to this power, plus this power, this power. So if you, these are all plus, this is equal, this is plus, and this is plus. See that one? And voltage is the same. The current also here plus this current. See how current adds up in a series circuit to the total current. The power adds up in a parallel circuit. I'm sorry, in a parallel circuit, the power adds up, the current adds up, the voltage stays the same, and that resistance is that mirrored resistance is went down. You get 600, 200, 300. The total resistor went down smaller than the smallest. About this circuit. Any question about this circuit? Joy friend and Matthew. This is the first ever time you're going to hear your friend chat talk about parallel circuit. And, you know, it's you guys on and you'll which is I'm going to go 2, 3, enter. Okay, so second example, guys. I'll leave this one. Any question about how to do an example like that? Any question? No. Me, Eric, my friend, Joe, you guys, keep yeah. Okay, now let's go to the second example. The example, when you parallel circuit, the most important thing is you find the best way of analyzing this circuit. That's exactly what we do, huh? And look at this circuit. These are in your book, as you guys know. This is in page 175. The I2 and R3. And I need to find everything else. See, there's R total and R 2 and 3, and we need us to find our total. This is tricky, very tricky. Here's the thought here. I will start, guys, by finding the key point. Now, the question would be, so where should I start, Chad? Where should I start? I'm going to start with this branch here, and I'll tell you why I want to start with this branch. The first, because I have the current, I know the current, and from the parallel circuit rule, I know the resistor. The key is to find two things about one branch. If you find two things about a branch, you're good to go. So if I find the voltage, if I find the resistor, I find two things that allows me to find everything else. Okay, so how would I start? I would start by 1 over 300. 1 over 300 equal 1 over 900, right? That is the rule. Plus 1 over R2. I don't know what R2 is. Plus 1 over 1800. 1800. That's the point. I don't know you guys, but if you heard the algebra, we need to find this unknown, right? This is unknown, R2. We need to find it. Now, a rule of moving. I don't know if you guys don't know how to arrange. This is R2. If you guys arrange the formula, it becomes R2 equal 1 over 300 1 over 900 minus 1 over 800. Okay? So, to find the common denominator, if you have a scientific calculator, you can go problem. You can go 300 shift minus shift 1 over minus 1800 1 over equal and then if you take the 1 over what answer, you should be able to get 600. So you should be able to find the whole our total here is 600. When you subtract all these, then you have to take 1 over the answer, and that will get you 600. This is so important for me. Now we have 600 things about one component, which is the greenly circle component. We found the resistor. Any question about how we found resistor? The R2. Question about how we found R2. If book 175, they're doing the same rule. They're doing the formula. The same. That one, you're doomed. So on R2, now I know about you, my friend Juan. If you know 60 and know 0.15, so you can tell me, Chad, piece of cake. Now I find E2, which is 0.2, times the voltage, which is 60. It's 12, I believe. Yeah, oh, yeah, 12. So 12 volt. Branch. Okay, found that this is a 12. And if I want to go directly to the power, P2 equal the same. You take the 12 and multiply by the 0.2. 0.2 times 12 equal 24 or 2.4. I'm sorry, 2.4. 2.4. This is volt. I found the power was 2.4. I found the voltage and the resistor. My friends, any has any question about that? Your hand is up. I'm going to go pass the mic to you. Go ahead.
Yeah, I think it's 0.2 times 600, isn't it? For any volt.
20 volts.
Yeah, 0.2 times 60, and the resistor 2 is 600. Not this.
Resistor 2 is 600. You are the best. Thank you. Off by 0. Thank you, boss. Yep, it's why did they get 60? Yep, you're right, 600. I found 100, yep, 60, and that will get me actually 24 here. Yep. This is the way. Yep, 24. Thank you for watching. Yep, 600, you're absolutely right. 600 times 0.2, 120 times 0.2, that will get you the 24 watts. Okay, so I don't know about you guys now. I found everything in this branch. Now, I bring to your attention one very important thing, that all the voltages are 120 now. The voltage and the voltage is 120 because of the parallel circuit, and this is 120. Now, if I go to this branch, I have two known things about this branch, which is voltage and resistor. I can easily find the current, and I can easily find the power. Same thing as if you come to this branch, piece of cake, find anything for this branch. So let me go and put my, and I'm going to go, guys, and move to the next step here. Next step. There you go. So we found the voltage 120, and R2 is 600. Voltage across all of them. Now, from here, piece of cake, guys, you can find basically anything you want. And attention from what they did here, just I'm going to do one little thing here. From the voltage to find, guys, as we all know, to find I1, you just take the voltage 120 and 100, and that's the 0.133. Right? And I2, I3, to find I3, you take the 120 by the 1800 this time, 100, and that will get you a 0.0667. I total, which is piece of cake 2, I total equal the 120 divided by 300, and that's 4.4. Okay, basically piece of cake. Any question about that? Any question? Let's continue with this circuit, guys. Go back. And the last one is the power. And I'm not going to tell you guys that the power, you find the law, which is voltage times the current. Okay, following, as I always have done, voltage, guys, stays a constant. Voltage, voltage, voltage. Can you guys see that stays constant? And then move into the current here equal the current here plus the current here plus the current here. Then, my friend, if you end up with a current different than what they add up to, I invented new science, or you made a mistake. So that's students. Either you invented new science or you made a mistake. That will be a checkpoint. You can check your work after you're done. You add all the amps. If they don't add up, then you make somewhere. And the second thing I want to bring to your attention, guys, is the power. The power, look at the power here, equal the power here plus the power here plus the power here. These are rules of the parallel circuits. The same thing circuit as a fact. Now the resistor, this is one. The resistor, if you test that one, go take 1/300 just to and check. Question mark here to check. Okay, 1/900, 1 plus 1/600 plus over 1800. Who made this equation and don't equal each other? They must have made a mistake somewhere. Somewhere you have just made a mistake, or you invented new science too. You can invent new science if you want to. Either or you invented new science. This is basically a very typical parallel circuit. That could be this could be your microwave, your fridge, your AC unit, AC air conditioning. All these tied together in parallel. All are tied together in parallel. To bring to your attention, guys, the voltage right in here stays constant. You can see that the voltage here constant, doesn't change. Okay. One, any questions about this circuit? Any questions? Make sure me. Thank you. So the next example, my friends. Check here. Okay. Let's take next example. Here's another example, and our example for analyzing circuits. Let's look at this example. Generally, the first thing you look is you have to see what given they want you to find. The first thing, that's the same important thing, is what they want you to do. What's needed? What's needed here is to find everything for every component. Okay. Now, always ask yourself, what are they giving me? They always give you enough information to solve it. Otherwise, it will. We call it as an engineer's unsolvable equation. Unsolvable equation. A solvable one, because we made a solvable one. I'm going to bring to your attention to what's given. I'm giving the power, and so, and I have the I total. I need to find the everything else. Tricky one, guys. I have the power, and I need to find that tricky thing. So I have okay. So I have the current, and I need to find. I don't think they're giving me the voltage even. They're not okay for power. Yep. Okay. Now the easiest way to solve this problem, the easiest way. There are two ways, guys, of doing anything. The easiest way and the hardest way. The easiest way, I know, guys, you heard Chad saying over and over that the total power equals this power plus this power plus this power, right? So the easy way is finding P total, which is the amount, adding the 0.075 plus the 0.45 plus 0.225. So if you add up, then the P total, you will find P total. And then when you find P total, guys, I don't know about you, it's not rocket science, but from P total, from P total, I can find E total, and I can find R total, and then with a lot of other stuff. I can find P total, so that's go. So if I find the P total is on the voltages and that one. Okay, I have the. Let me get. I need to put P total. And in this case, guys, if you add all these together, you should come up with a 0.75 watt, 0.75 watt, and then find E total. If you piece of cake for E total, with E total, it's going to find the power, which is we found it is 0.75. The current, which is given as 0.05, which they're here for me, unit 15 volts. With P total and the E total. Anybody any question how to come up with P total and E total? Why start with the P total? Because that's the single easiest way of doing business. The single easiest way of finding it for this circuit. Any question is E total, P total. I don't know about you guys, since we're in the totals, let's find R total. So R total, just for the heck of it, R total, we know that R total equals E total divided by I total, right? I total. So I can have 50 divided by 0.5, and 15 divided by 0.05 equal 20. So this will be 20. Now done completely, utterly. I'm done with the branch that has the power source. I'm done with the power source branch. And for the power source branch, any questions? So total, P total, E total, any questions? Okay. Before I leave this one, I want to bring your attention the link. By doing this, I want to link that between this branch and is the voltage. Can you guys see the voltage? The voltage stays constant. The voltage stays constant. The voltage stays constant. So basically, I found that my voltage is 15 volts here, 15 volts here. Now we'll go analyze this branch. I know you guys, if I want to analyze this branch, I know the voltage, I know the power. Can I find the current? The current one, for example, equal the power. We have the power is 0.075. If the voltage, right? That will get you if you the I. So 0.075 by by 15, and that will give me 0.005, I believe, something like this, 0.05 amps, 0.05 amps. Any question? So I find one, and let me just let's find R1, guys. R1 equal, basically really piece of cake. You're going to find the voltage, which is 15, and by the current, which is 0.05. So basically 15 divided by 0.05, and if I did my math right, I'll give you 3,000. Anything else? Any question about that? Let's just do that one here. Okay. So, and next step, since you're masters, now look at the voltage. We found the voltage and the power. Can you get that? First, we found the power. Find the voltage. Piece of cake from the power. and the power, I found the current in each one of these branches, and from the current voltage or the power and the voltage or the power and the current, I can find the resistor. So for the last time, attention guys, the voltage stays the same. You guys look at that one. And the second thing I'm going to highlight is the current adds up equal this current plus this current plus this. Did something different. Have invented new science, as we said. Here's the power. The power, the same thing, equal this power plus this power, or invented new science. And last but not least, my friends, is resistor. The resistor equal this resistor over this and reciprocal. Reciprocal. And here you go with a third parallel circuit that you guys have analyzed. Any questions? This one, this would be my dish. This will be garbage. This, and this will be garage door opener. Pieces of equipment connected, guys, in parallel across the involved source. Any questions? What? Okay. Let me and get the track. So let's go, guys. So we went over, guys, example number 6, 2, and example number 3. I didn't see that one. I must take a look with the calculator. Chat. I should have been looking at my chat. I don't know which example what that related to. Let me just look at my example. You chat with me to which example? Never mind. Okay, you got it. Okay, I got it. No problem. Thank you. I'm sorry. I didn't been looking at the chat. I didn't see your chat. One more time, guys. Any question about analyzing the circuit? Again, this or you get it. You got it in technical colleges probably. If you got into technical, which a lot of you probably did, we spend months teaching students parallel series circuit, DCC. So we burn a couple of meetings. I can't emphasize, Eric, the best thing to analyze circuits is basically to do it over and over again. Really, if you know the system. Okay. Guys, the 5 rules of a parallel circuit, or 3 rules. Look at it. A parallel circuit has multiple paths. The parallel circuit adds up to the source current. The circuit stays the same. The power up to the source power, and the reciprocal, the sum of the reciprocals of all the resistors in the circuit equal the reciprocal of the total resistor. That's basically a few things. There's a few rules, shortcuts, a few understand, guys, about parallel circuits. Few shortcuts. It's called the current divider. The current divider, friend, is the following. That is, would actually, as a matter of fact, take the smallest amount of current. Very nice. If you have a resistor or a load that's so huge, resistance is the smallest amount of current. And the reason behind this, because the current seeks the least resistive path, So, if this resistor, just by looking at it, if this resistor, guys, was 100, and this just 1, which one would you think that will have the lowest amount of current? Can you guys chat with me? Just by looking, R1 is 1 ohm, R2 is 100. I think we'll take the lowest amount of current. Is it R1 or R2? Just by looking at it right now. Which one is it, R1 or R2? I know current, not voltage. There's a lot of people that get confused between current and the voltage. The voltage is absolutely right. The fastest, biggest resistor will take the largest amount of voltage. Current is really the opposite. So I see 2. How many? 2. 1, 2. What's going on here? Make up your mind, guys. Either 1 or 2. All right, do that one. So if this one again was 100 here, and in fact, guys, the low amount of current will go through the skinniest. So current coming out of here and here, come here. Now most of the current is the least resistance, which is go 1 all the way back to the source. Okay, that's a current. Oh, what? Some little amount of current will in fact go through this. You see that? The current will go through 1 and back because the smallest resistance, very resistant. And current here, that's through this one, is going to be 1%. The current go through here, so 99% of the current. 90% of the current is going to go through the smallest resistor, and only 1% is going to go to the fastest, biggest resistor based on this example. Which means if I have 100 amp, well, guess what? This 1 amp going through this, and it will be going directly through this one will be 99 amps. That you can see. Okay, so this concept, guys, is called the current divider concept. The current divider concept. Any questions before we write the formula for the current divider? Any questions before the current divider? It actually makes calculation easier. Here's the formula for the current divider, and I want you guys to look at it clearly. Here's what it says. These are in parallel, and the current is IC here. One of them is IX right here. In any one of them, could or be here. Any one of them, IX. I says RX. BR also RX. RX. So two different ones. And the X equal the R divided by RX times I. So this is the opposite of what the voltage divider is. Take a quick example here to what we're doing here. Example is right here, guys. If you look at 3 resistors, now by 3 resistors, I want you guys to look at these 3 resistors and check which resistor, just by looking at them, it's going to get the largest amount of current. Can you guys type the resistor number that's to get just by looking at it without doing the math? Don't do the math. One of them, by looking at it, will have the largest amount of resistance. Okay, chess, which one is the largest amount of resistance? Still used. The largest amount of resistance is the one that has the smallest resistance. The smallest. I think you voltage. Don't think voltage. Think current. Think current. That's going to have the largest amount of circuit current is the one that's going to have the smallest amount of resistance. But this is the most important concept in the power industry, because circuit, what happens when you have a short circuit? When you have a short circuit, a huge amount of current, short circuit, breaker. That's exactly what's going on, because the short circuit has the least impedance. Through the least impedance, which is through the ground equivalent conductor back to the source, so fast that will immediately trip the overconduction device. This concept that you're looking at. Oh, this resistor will have the largest amount of current. This resistor must have the largest amount of current, or you have invented new science, which is okay. So using the voltage divider, here's what it goes, guys, for the voltage divider. Suppose I want to find I3. Now, we have two options of finding I3. I do analyze the circuit, guys, based on what we've done in the past, and you find I3. Here's I find I3 if I want to. If I find the voltage across, if I find the voltage here, and I find the voltage by the resistor, I can find I3. So two ways. Either to find the voltage V3 and I guess no problem, you can do that. You need to take these two together and from find V total. V total equal basically 280, and this my math is 160 volts, right? Same as V3, right? Parallel circuit, hello, 160. So that will give me 160 here. Divide this one by 120, right? 160 divided by 120 equal 0.33. Equal 1.33. Okay, method done. Joe, you're done. That's method number one. If you use the voltage divider, it's supposed to be faster and quicker. The voltage divider, I'm going to use blue here. If you get the blue, I3 is the total. The hardest thing to find the R total equal R total R3 multiplied by I total. Relations here. I don't know what R total is, but I know 3 is 120 is 2 amps. And I need to find the R total. The calculator, if you have a calculator handy like Chad, R total, guys, equal 1200 1 over 1200 plus 1 over 300 plus 20 1 over 120 equal 1 over the total. And guess what? This is actually 80. Where the heck come up with the 80, guys? You're going to find, remember the R total, how you find the R total? R total equals 1 over 1200 over 300 over 120 with R total. Okay, so based on this, guys, you make 80 times 2 divided by 20, and surprise, you came up with in the same answer, 0.3 amps. If you came up with different answer, you have to check your calculator. You have invented new science. Voltage divider. And about using the voltage divider. This is 1.33. This is I3. Let me just tell you guys. Let's do one more example here. Let's go the fattest one, I1. So I think, guys, is 80 divided by 1200 times K, right? 60, right? Divided by 1200. That will get you, that will point 1.33 amps. 3. Now 1.33. So we know it's 10 times less. 10 times or divide. It's like divided by 10. Okay, for this, and it's just for the heck of it. You guys go and I'm going to find the last I, which is I2 equals 180 divided by 300 by the 2. So 160 divided by 300, that's 0.53. Very healthy 0.53. Now, if amps, let me go to my red and grab my big letter. If you add this amp to this amp, so add together, add them up, you must come up with this amp. That's the rules of a parallel circuit. You can't violate the rules of a parallel circuit. Questions, Dan, JC, my friend, Matthew. Of a parallel circuit and the voltage divider is extremely important. As I say, very, very important. Okay, we'll guys give you the poll for the night, and we'll talk a few things. We'll give you a break here after my first poll and last, as a matter of fact. So let's go. All right, go over my poll for the night. It's 9. Okay, 9. Calculation with the options I have. Let's give it minutes. You're able to get finished earlier, guys. Okay, let's go ahead and chew on that one, guys. For here, I give you, and you get asked. Circuit then makes you a better electrician. Yeah, sit and argue a little bit, but we do one thing for you though. It's your license. A good electrician, it will make you a better electrician. But if you don't know inspires and all this stuff, it's not going to teach you how to do that. System better, I think, anyway. almost done, guys. I know some of these calculations might take you longer, but I trust you guys will do the rest at home on your own. Great. Almost. Okay. Let me just share this with you. Apply, correct answers. See who submitted. Got it. So if you look at 4 or 5 and a couple of them, if I give you the current and you add them up, or give you the voltage and give you the resistor, all the resistors are the same, and you find that you divide the total resistor divided by the sum. So question number 9, the last one, guys, is a voltage divider question. So you find the total resistor and you use divider rule. That will be the easiest way of using it. Solve number 9 with any method you want. Voltage is the best. So that's what I want to highlight here. Anybody has any questions, guys, about the poll? Any comments? Any questions or comments about the poll? No questions? Okay. What I'm showing you guys here as here's what the situation is, and I want you guys to chat this with me. I have 100 resistors, each consuming 10 amps from them. What is current? What is the total current of the system? How about this one with me one more time? I connect in and 10 amps. How much total amp the system? I see a lot of nice numbers here. One more time, I'm going to give you a few seconds. 1 resistors connected in parallel, each one of them consuming 10 amps. What's the current of consumed out of the system? One more time. I need to hear from more of you guys. Perfect. So that's it. Thank you. So again, 100 resistors, 10 connected in parallel. What would be consumed by the circuit? Let's look at that one. This is really an interesting situation where I total equals F, which is the number of the resistors in parallel, multiplied the current in any resistor. So you take the 100 and 10, because each one of them consumes 10 amps. That's 1,000 amp. The right in here is going to be 1,000 amps. And this is kind of a rule, a short rule. If all the resistors are the same, Action about that. So resistors are the same. If current in every resistor multiply the number of the resistors. So that one. Okay, question asked one more time. Any questions? Any questions? Friend, Joel, Matthew, Ross. Okay, with this, and before I move to the second section of my stuff, what I'm going to do, guys, I'm going to give you a 5 minutes break here, and then we're going to go to the generators and the transformers, the exciting stuff. So what we're 8 on, let's give you 809. 809, that'll be good. Okay, let's take a few minutes break here. And motors in parallel and so forth. can check in, make sure you're back. And all right, I'm going to share with you a few things. One is parallel. If you do one, this parallel power sources. All what you're looking at, these are power sources, batteries in this case, power sources. In a live situation, parallel circuit, you can use it to connect loads in parallel, and also, and we studied this one, you just went through connecting the microwave and plasma TV and everything in parallel. We connect power in parallel. So I want to pay attention, guys, the following. If you look at this, is a 12 volt, the one 12 volt battery 2 volt battery 3. They're connected in parallel, so you put the positive to the positive to the positive, and you connect them with the blue, the negative to the negative, and connect them with the green. Bring to your attention that the batteries are 12 each, and each one is pumping amps, 10 amps, 10 amps, 10 amps. So genius to understand the current coming into the here is actually current right here is 30 amps. Can you guys see that? Everybody can see that this is a 30 amp current. 30. So we're resources of power in parallel to give us more amps. Load, L stands for the load. That now this load, guys, is connected. If I want to find the power for this load, the P for this load right here, the power consumed by this load equal the across the load, which is 124, by the power across the current across the load, which is 30. It doesn't take a genius to take 30, multiply it by 24. You get 700 and watts, 720 watts. By putting four in parallel across a load, each one of them is 10 amps, I have achieved a 720 watts. You have applications and especially wind, solar, and so forth, where they can parallel batteries, series get you the voltage, parallel them to get you the amp, the higher amp. So, say, Chad, well, who cares? Well, if you just only put one battery off this load, let's just say just one battery, so this will give you 24 volts, nothing will change, except amps is only 10 amps. One battery is only capable of pushing 240 watts of the system. That's where the power of paralleling generators and resistors. So Eric, my friend, we went from system that can deliver 240 watts to a system that can deliver 720 watts. Is that a deal? Yeah, you triple the amount of juice inside the panel. Literally triple the amount of juice inside your panel. That's what we basically call it paralleling generators. You're absolutely right. I said 12. Well, since I made that mistake, let's just change these batteries into 24 volts. How about that? 24 volt batteries, custom designed for us. Since we're calculation, let's make these 24 volts, 20 volts, and 20. Now, right? My friends. So we choose 24 volt batteries. What about this? Any question about how to parallel power sources to get more power? They're cool sources, guys, for a reason. Eric, my friend, we can put that power in series and get more power. When we put them in parallel, I want you guys to keep in mind, when we put them in parallel, the voltage has to be the same. For example, can you parallel a 24 volt battery with a 12 volt battery? You can't. The voltage of the two sources have to be the same. Can you get that? Everybody can see the voltage 24, 24, 24. If you put parallel. The current, guys, for the first could be 10 amps, the secondary 20 amps, but the voltage must stay the same. So one more question about paralleling DC power sources. DC power sources. See, why would we parallel? We triple the amount of power by paralleling, by putting them in parallel like this. 3 times more power for the same amount of voltage. For the same amount of voltage, 3 times power. That's the reason why we parallel. We parallel resistors for the same reason. Okay, so let's go to the AC. Now, AC situation, guys. Let me explain this one to you. This is a 2 meg. Well, it's just work. I know it's going to be. I'm going to change these one from a meg, guys, into a 1 meg. This is a 1 meg generator. 1 meg, 1 meg. One of these 1 meg, and this is a generator. Okay, so meg generator. 1, 2, 3, 4, 5, 6 divided by 480 divided by 1.7. Okay, and then 0.8 roughly. Okay, so let's say these generators, the voltage in this system, guys, is 480 system, 480 volt system, 480 277. Okay, now each one of these generators is capable of pumping a 1500 amps. 1500 amps. That's very typical generators. So this is going to be pumping 1500 amps, and this will be 1500 amps. 1500 amps. Okay? 1500 amps. So if they reach this point, I don't know if you can put these 15 amps times 3, that gets you almost 44, which is, you might not get that one. So all up together, guys, you're going to end up right in here with a juice equivalent to 1,500 amps, close to 4. There's no switch 4,500 amps, so you might put these all operators on one at voltage anyway, at this voltage. You might put them at different voltages. So when you tie them together through a switch gear, mid-voltage switch gear, have achieved a 4,500 amp worth of juice. 500 amp worth of juice. Now, you're going to say, well, Chad, they don't make, well, they use more than 4,000 amp switch gear. Yes, but in a real situation, you would see 2 of these, not 3. You see 2 of them. So let's make it more realistic and get rid of 1 inch here. Let me make it more realistic so it can kind of more. I'm going to get 1 branch. So in case like this, my friend, you attach yourself a 3 amp switch gear. That's very common. 1,000 amp switch gear tied to it 2 1 generators, and for the other side, so my switch gear here is 3,000 amp, 80. And then here, guys, I can feed my loads. I'm coming and feeding panels. This is my this control center here. This is my chiller. I have chiller here. I have all mechanical equipment, oil equipment. So this is a 3,000 amp switch gear. From one side to 2 generators. From the other side, multiple loads are fed from this 4,000 amp switch gear. This is, friend, what paralleling means in the power industry. Saying paralleling generators, right? How many have heard the term paralleling generators? Paralleling generators? Nobody? How many paralleling generators or generators? That's what they mean by paralleling generators. You tie them together. You tie together. They're acting as a 1. They're acting as a 1. If you get into that paralleling generators. Why would parallel generators? Because it gives us more power. It gives us more power. Just to give you an idea, guys, when we parallel these 2 generators, if I have 1 generator, it will be only 500 500 amps. If you multiply this by 480, 500, and multiply this also by 1.73, that's basically the amount of power that you're going to get. And you're going to get something, if you 150 and 100 multiplied by 480 times 1.73, because 3 phase, equal divide by 1,000 to get the, you're going to get equivalent. Don't forget to divide 1,000 to get you the kV. Get equivalent to kV equivalent to 1.2 megavolt amp. Mega, not K. Megavolt volt amp. Okay. So now by doubling them, when I put 2 generators, what's what happened? I doubled the amount of juice, the volt amp. So the second one, now we have 2.2 megavolt amp capacity in my system. That's easy with parallel generators. So that will give you an idea of why we parallel our generators. And you guys about parallel generators? Anything about paralleling generators? AC or DC to get you more power. And Brenna, my friend, you might, it's not parallel, but physically, mechanically, guys, when they tie them, here is A, here is phase B, here is phase C, at neutral, my phase A is my phase B, and this is my phase C, and this is my neutral. When the generator, guys, these are the terminals of this gen, right here, A, B, C, and this is the terminals 1, 2, 3, 4, terminals of gen number 1. What you do is physically take phase A side to phase A from this side to phase B, from they go to the same thing, B from here. And can you guys see how they are parallel, tied together at the other end? And this to a different color here. And C side from this side to this side, and the neutral is tied from this side to the neutral, from this side to the neutral. That's what it means. That's the structures. And for what's inside these generators, guys, if anybody's wondering, right here, there will be right inside them. Let me just sit here. This is the delta, so the winding here going here, and where's the other? Here's the other phase going here, and the neutral to the center. So right inside it's going to look like this, and this way, and phase B going this way, phase C going this way, and all the way my neutral, which I'm going to use this one for it, going right here to the center. So that's putting the conductors together, paralleling gears. And if you guys look at the coils actually mechanically, look at the coils of each one of them. Let me just, I don't want to do coil number 1 is the coil number 2 is number 3 for generator number 1 is the coil number 1. Coil number 2, coil 3 for generator number 2. So look at when you parallel them, and that's 3 phase, so it's a little bit interesting. You tie these two together. So these coils now are parallel, and you how do you do that one? You tie these two together, and you tie these two together. So, and you also tied together. So I want you guys to look at how I'm just going to see. You guys see this here? These are actually these two coils, and these coils are actually parallel. And I don't know if I can get over these. And these two coils are actually parallel. Parallel coils to get me to get any question about parallel coils, which is in generator. They're parallel. The question about that? What I'm and just try to convince you how important the concept of parallel circuit is, not just, you know, using it and so forth. Dan, any question, my friends? Any that concept of how to use generators and how to parallel? Let me take you guys to another important application for generators, which is motors. So we talked about generators. Let's talk about motors here. This is in your journal exam, no question asked. So you have let me I don't know how many of you, probably if you went to technical colleges, you have seen how they make deltas. They make this, guys. Let me just erase that one. Let me show you dual. Let me ask this. How many of you guys have heard the term dual voltage motors? Dual voltage motors. How many of you heard the term dual voltage motors? You probably see them all the time. 240, 480, 3-phase, and so forth. Dual voltage. Oh yeah, by the way, you can connect them to two voltages. How do you connect them to two voltages? In a single phase, it's just a single phase motor, guys. If you phase motor and I'm just winding, here's winding number 2. This literally physically they make 2 windings out of them. We call it a start winding. Just don't look at the back one. So I went over it last time. If you connect, if it's 20 volts and this 20 volts and this motor at 120, guess what they do? And also this one is 120 volts. 120. They add enough coils to handle only 120. So guys, if you grab this here, take it all the way to here, and you parallel. Okay, you can see how I'm going to be paralleling, and you grab this leg here, take it on here, and you get yourself a 120 volt motor. 120 volt motor, and of course this one has to be tied to one leg, the start coil. It will be, say, let's just say 1 horsepower, 1 power motor. Connecting the coils in parallel, I can run the motor at a lower voltage. The motor, you can run it at lower voltage. So it actually is a 120/240 motor. They call it dual voltage. 1/240. To run them at 120. Now, how do I connect them to Chad if I want to run them at 240? You series them. You guys remember how we did with the series? This is a different color. Hopefully that wouldn't confuse you. If at 240, look what I'm going to do, guys. I'm going to go tie these two together. These two ends tied together. Can you guys see that? And the voltage from here and the voltage from here. Now, right in here is my 240. Look at the green. If you do the connection with the green, whether or not, you take 2 parts of coil, wire them together, and the other side you bring it to the 240. Now my motor is running at 240 and still a 1 horsepower motor. Why on earth would they do something like this, Matthew? Because they give you one product that you can use multiple voltages, right? One product, one motor that you can hook. If you only have 120, well, 120 no problem. Rehook it 120. If you were running at 240, no problem. Rehook, reconnect the windings to the 240. So that's 40. But when you go to a bigger system, I'm going to show you 3-phase. It makes more sense, guys, when it comes to the 3-phase motors. Actually, it has about single phase. See the coils in series to get some voltage. Now this the same. I want to bring to your attention now. The power is still the same from the motor. The same motor still for the same amount of power. Generators, guys, we wire them. We add different generators to give us more power. The coils inside the motor, not the motors themselves. The coils. When we rehook them, we can get different. And actually, the generators, they can do the same thing with generators. Let me show you phase, and a three-phase delta motor is easy, guys. So I'm going to go, here's a three-phase delta motor, and you're going to build over this with and this is the winding. It comes by manufacturer, guys. It comes with 3 coils, 3 each one of them. And just say each one of these is 120, or let's just not 120, 240. We'll use each coil is actually a 240 coil. This coil is 40, this coil is 240, and 240, 2 Chad, 4 at a 0, 240, and 40, and the last one is 240. Okay, so motor. I'm going to be pushing, guys, the following. Here's motor. Here's phase A. Here's B. Here's coming to me. Now, if I want to connect this motor and high voltage, all we have to do is tie these two with a wire knot. Tie the wire knot. The wire knot. Now, this motor is running high voltage. Add the 2 voltages together at 480. You yourself a delta 480 motor. You get a delta 480 motor. Look at the coils. The coils are connected in series now. Now, if I run the same motor, I went to a building and the only system that is 240 3-phase. Okay, then you can connect them, and this needs some some explanation, guys. When you connect these, and it might get messy here. I bring this coil to this end, and this coil to this end. Okay? These 2 coils now in parallel. The same, if you take this coil to this end, get rid of the red. Don't worry. And this coil to this end, and you just examine the hookup for them. This to this end, and this coil to this end. Okay. If I do it this way, I don't know if you can see, guys, but these 2 coils right now, right here, these coils are actually in parallel. What it means, you just put coil 1 and in phase, and you tie them together like this. That's what we've done. In every phase, you put the coil together. So this becomes 240, guys, right? And this is 240. If you do it this way, then the system will be a 240 3-phase system. 240 3-phase system. So I have one, and this, let's just say this is a 50 horsepower motor, right? 3-phase 50 horsepower motor, commonly used, right? You can use the air handling unit, so forth. Horsepower motor, I can at 480 or 240, no problem. It's going to be different, Eric, in the amount of current that's going to consume. If it's 40, it's going to have more current. If it's 480, less current. Power, though, stays constant. The amount of power that's going to consume from the system is constant because the power is 50 horsepower. 50 horsepower. You can run it like if you have a 50 pound load. If you carry the 50-pound load in a bus or 50-pound load in a car, you still achieve the same thing. You know, a car. That's the voltage is like a bus or a car. Think of it this way. The same. It's still a 50-pound load, 50 horsepower motor. But to energize it, you use it at different voltages because these are the voltages available in your system. What has about this and this, and I don't. This you're going to be studying this in 4th year. I'm sure if you went to technical colleges, which a lot of them did, we just went in and done it. We teach in 3 months: motors, generators, and transformers. It's really interesting. Any questions? So that is the importance of a parallel concept of paralleling coils. Brian, my friend, when you parallel coils, you get lower voltage. When you series them inside the same equipment, you get a high voltage because of the coil. You add a coil. Now, here's where I heard about this. Here's what Brenna and Byron and Dan, you have a motor like this with 9 leads coming out of it, and the voltage, it says 480 240, and they want you to hook up this motor to hooked up to 240, right? Hooked up in parallel like this to 240. And if what happened, Brenna, if you go grab the leads of this motor that's hooked up to 240 and you plug them into a 480 system, you have your piece of equipment. That's why motors, brand new motors, the first thing you need to know is to look at the wiring diagram for them and become dual voltage. You look at, is this a 480 motor? Yes. Is it 480 motors? Yes. Now we're good. Is it for 240? No. Then we have to pay attention to it. Interesting. I saw people, electricians like yourself, burning equipment because they pay attention to the seriesing the coil to get higher voltage or paralleling the coil. I think if you series them and you go put it in a 240, Brenna motors are dumber than rocks. If you give them a 240 volt wire 480, they will suck more current to compensate for the loss of voltage, and in the process they burn themselves. You don't want to burn a 50 horsepower motor on a piece of equipment that's expensive. That's get lower voltage, we seriously get higher voltage. Any questions about this? I true because parallel series circuits sometimes when I was in college they never this way. They do all these and they start monkeying around with these numbers, and you start thinking, what are they doing? Why are we doing this? We're doing it important. That concept of parallel from generators to batteries to motors to transformers is a very powerful concept. Very powerful concept. Basically, in terms of transformers, guys, it's the same thing. You can a good example. I'm trying to think of a good example of a transformer. Let's use the single-phase transformer that we use all the time. Here's one coil, and here's another coil, right? From the other side, transformers, the 7200 high voltage side of a transformer, utility side. So in this side is this is the typical what we give to residential, right? They tie these two together, or center they call them, and here's your hot one. To the other side, this is hot 2. Up to this point, no problem. This coil is rated for 120 volts. This coil is rated for 120 volts, right? You, Brenna, my friend, but I'm looking at a series circuit. Don't you guys see on the secondary side? Don't you guys see this coils are connected in series? You're looking at a series circuit, okay? Then, if you to get from voltage, the smart and Chad, you can grab a wire right from the middle here, and that will be your neutral. And what is the voltage for us, just to make it sure it's always 120, they want to connect it to Mother Earth. The system, that's the ground system. You ground it, but it's making it more stable when you ground it, the 120 to ground. So that's an example, guys, of a series circuit. That you can get from a transformer. Now, why would I bring something like this? Now, what if I want to make this transformer on 20? Look, doing is going to confuse you, so don't sweat too hard. I can go and take this lead and this lead, get rid of the voltage between the two hots. Between the two hots is actually 120. Please don't get confused. If I'm in parallel, so what I did, guys, I brought coil 1 and 2 and then 20, and that hot 1, 2. You can do that, no problem. Hot 1, hot 2. So that you can where you can get In transformers, Jacob, my friend, the coil used to create more voltages, like 2 voltages, like 120, 288, 480, 277. That's the concept that they create. Unlike motors, they're and also in more created to give more voltages, as a matter of fact. Not more power, more voltage, more up of the equipment. That's I do a 3-phase transformers, and usually can come up with a different configuration. It does a whole lot of sense to parallel coils for them. Really, 2 voltages in them. Already have 2 voltages. Those are transformers who have 2 voltages, guys. So you can have this is just showing the single phase part of it. You can have 2 voltages, 3 phase. You see, I've seen these for 69 kV from this side. From this other side, you can take 60 for well, you can get one as 12.47 K in 1 kV, and 4.16 K V side. These are, I'm just showing single phase part of that. So you can get 2 major voltages out of the same transformer. So, and they do that one, guys, by seriesing and paralleling the coils in some way. But we'll go deeper into that one and confuse you more. After this, and about series and paralleling, coils. So remember, we talked about power sources, transformers and motors, paralleling transformers, paralleling motors. That's my mind. Advice for all of you guys is series parallel circuits. Them to go to your test, and after that, it just makes you a better electrician to understand how the system is put together. And one example I always like to show with my students, I show, for example, a load, a very simple load like this, a lining fixture, coming from the panel. This is my neutral. Is my, it just say 15 amp, just a 15 amp, 120, very simple, typical. And say that the circuit, guys, is carrying, the circuit here under these circumstances is carrying 10 amps. 10 amps, okay? So normally 10 amps will go through, right? Go through the load, burn the load, and come to the source, the neutral, right? So we should do it. So right here, and hit the neutral to the ground. Right? To the ground. Now, when neutral to the ground, if you guys look at the they just find R of this equipment, the 120 is 10, actually at 12 ohm load. 12 load. Now, the resistor, guys, the only thing left, look at that, from here, all here, all back, the resistor of this load will be very small, very, very tiny. Is probably, I'm just going to put a number here, 0.001 ohm, 0.001. So the current is going to go, right, most of the current is going to go right through this resistor, right through the deck. So you're going to take 120, look at that, you're going to take that 120, divide it by the 0.001, right? There's nothing, because all the current is going to go through it. So we have 120 divided by 0.00, with this 1 equal, and you cut yourself, if you 1 divided by 0.001, you got your 1, 2, 3, and 20,000 amps. This is big. I probably should get rid of 1 just to make it more realistic here. Get rid of this, so get rid of 1, 0. Okay, so if you have a resistor, if you get rid of 1, 0 here, 0.01, so you divide 120, guys, 120 divided by 0.01 impedance, you get yourself 12,000 amps. That's the short circuit. That's what you see with a short circuit is. The circuit breaker amp is going to trip. So it's a parallel, and most of the current is going to go, 99.9 of the current is going to go through that side, because if you look at the impedance, 0.09 compared to a 12, it's a small impedance compared to the, so we the load. We call it the load. My friends, so that's where you look at the more current, almost all the current is going to be right through the baby here. Will go right through here with small amount of current, if any, will go through the 12 ohm, because the impedance 12 ohm is so high compared to the 0.01. 1 compared to the impedance is nothing, guys. So if you take 12.01, so 1 point is 120 times more than just 12 ohm is 1200 times more than 0.01. So the current is going to be 12 times more, of course. We have here for this, very good point, Byron, my friend. The practical use, very good point. Well, who cares? Well, I want to tell you that you care all the time, guys. If you look at a circuit, if you go up, look at the circuit breaker has 2 values. If you 10K, they will roughly rating 10K. Most of circuit breakers. If the circuit breaker is 10K and the available short circuit is okay, you have burned your circuit breaker, Byron. That is very important. Well, it explains why the short circuit goes so high, because of the low impedance. And 2, every circuit breaker, guys, have a 15 amp. If you look at the 15 amp at 10K, they usually 10K, the small one, 10 kilo amp. Meaning up to 10,000 amps, they're capable of fighting. If you pump more than 10,000 amps, you have just burned them. So that, I don't know, make it, but that's very important in a short circuit calculation. And so forth. Anything else about the parallel circuit? But our parallel circuit, so I don't want to diverge it too much from the parallel. Just like the example, because it shows you how the current can be shunted away from the load and be very high to trip the circuit breaker. Okay, question is about this. When I'm controlling sources, in the past, guys, there's a couple of them here as examples of really interesting certain answering some questions. I want to bring to your attention a few things and ask you in a few minutes here left. Let's just here. I want to bring to your attention, guys, that this side here, C, so there could be in parallel or could be in series. You can put the system in parallel or you can put them in series. You can put them in parallel. So here's okay. So this, a couple of questions, guys. If to close, let's just go. We went and we put a 30 amp DC. Okay, I powered it with 30 amp DC. Even if I close this conductor, the circuit breaker, and close this circuit breaker, this switch. Do I have a series of parallel circuits? Can you guys see it? Do I have a series circuit or circuit. So you have a series circuit in this case or a parallel circuit. Anybody? Let me series parallel. Can you tell me what do I have, a series circuit or a parallel circuit? Series. Can you help you track the current? The current came and through for the current. Ignore the voltmeter. Ignore the voltmeter. This series of parallel. You guys can see this is series. Series circuits, right? And probably some of you guys this voltmeter. Well, yeah, this is the voltmeter is instrument. So don't worry about voltmeter. Ignore the voltmeter. This is series. Now, let me ask a question. If this is R and let's say a meter. Let's say in this case, oh, this is a meter. Let's say these one R. So that's series. I see why they're parallel. It would be these boring and okay. Just okay. Let me just ignore that one altogether. Now so if you just close this one, guys, and close, it's really basically a series circuit going through the meter. Just it's our meter, so we don't get confused with them. So let's go, guys, and power. Let's close this one and close this. Okay, in here and split. And we'll grab my power from the other side. Grab my power from the other side. Okay, and go to the source. Go to the source. See, I close that one. I went through the source, and this is just a meter going through. Okay, you can see that this is a parallel circuit. Parallel circuit. Now, for you, if this is an R, and this, if this same, okay. First, what's the voltage across each one of them? What's the voltage across each one of these resistors, guys? What do you think the voltmeter will read here? If 30 volts, what would the voltmeter read? 30, Chad. Duh. Okay, now let me tell what is the same? What do you think that if the resistors are the same, do you think the current will be the same here? You guys, resistors are the same. Would you think the current that's going through each one of them would be the same? The current through them, if the resistors are the same, the current going through them would be the same. Now, if this is closed and this is closed and this is open, you think that these lights will go on? Can you guys look and tell me if this will go on? Only okay, just where the power came from here, came to the source, came to the source. Oh, there is no return. There is no return to the power, right? So I don't have to have return, guys. There is my return tied through them up to this point, and it sits there. And this is from here. I need to close this circuit breaker. So this circuit, if this switch is open, I lost my neutral. I don't have a neutral on this case. So the only thing that you can make the system work is if you close that one. If you so that was a good teaser anyway. Here's how I always like to look at them. I always personally like to the hot look at this hot side coming to the should, because we always switch the hot. It's hot. I will bring hot to the resistor, right? That's the switch hot. And the other side, I'm going to bring my neutral from each and every one of them, right? Is that what we call it all the time? In DC or AC, whatever. I don't use the neutral normally, but this is for experimental only. We're bringing a 30 volt. So this system is, and don't pay too much attention to these. These are, my friends, are just equipment. So don't switch apart this little thing here. Ignore that meter and ignore that meter here. Think, the meter. Not next week, the week after, guys. Meters, we put them in series if they're ammeter, impact meter. We'll talk about this one next week. Okay, but just looking at this, and I'm going to go quick here, and if I close this circuit, and this circuit, do you think I have power? How many of you guys think I have power if I close only S1, S2, and S3? We can't. Why? Because I have to close S4 chairs. So let's go ahead and close S4 and have a question. Okay, close S4. 1, 2, and 3, and 4 are completely closed upon 30 volts. I wish this is where we can do measurements on it. But look at it this way. I want you guys, by looking at the circuit as is, all switches, I want you to tell me which resistor will have the highest amount of volt of current. We'll do any math. Which is the highest amount of current? Okay, great. Now that's good. So resistor R1 is going to have the largest amount of current, and if you why, because lowest amount of impedance. Here's which resistor is going to have the largest amount of voltage? Which resistor is going to have the largest amount of voltage? Which amount of voltage? It's a parallel circuit. Voltage stays constant. Good one. So in a parallel circuit, guys, all of them share equally same amount of voltage if they are hooked up in parallel. The same voltage. Okay, that's basically it. Now, if I am to go and open this, and I open this, okay, and grab Arturo. When I open S3 and S2, do you think Arturo goes up or down? When I open S2 and S3, do you guys think Arturo goes up or down? Again, I opened S3, S4. You want to find Arturo. What happens if you open S2 and S3? Does it go up or down? That you will see your circuit, guys. Which is 1 over RT equal 1 over R1, 1 over R2, and so forth. Let me hear from you guys. I have from 3. I need more. Does it go? Come on, guys. Down. Oh boy. Okay. Well, if we open S3 and S2, let's just here. Look at this one. Look at this way. Here's R total, just to help you. R total equals 1 over R, 1 over R2 plus 1 over R3. So to help you understand, open when I S2 and S3, basically I got rid of R2 and 3. So it becomes smaller, then R will go up. R will, for example, if 1 was divided by say 10 and get rid of something at the bottom, it becomes now divided by 5. The over will go up. So that's where it's not doesn't go down, it goes up. Open, when you get rid of resistors, the all resistors, the system goes up. Now, here's my tricky question. Now I went back again and closed these circuit breakers. These things, guys, happen to R2 when I use S2 and S3. Does it go up or down? Now we're doing, hopefully that's an easy. We're doing the opposite. When we close these, guys, okay, close them, this means I added these again. I added the resistors again, and definitely R2 will go down. Okay, so that's basically what I wanted to share with you guys. We're going to be talking about parallel series circuit. I hope I did not bore you to tonight. We're going to put the two together and talk about a complete grid system, national grid, building here, how the real application Brenner in a building is. But series and parallel circuits, series for the conductors and the fuses, parallel for the loads and the power sources. That's basically summarize the whole combination series circuit. Do some analysis of that. Oh, anything else before I let you go? It's 9 o'clock. Respect your time and mine too. How about an extra chair? Just done your homework. Please email me. We're getting closer. We have four or what is this is 19. We have 5 more meetings, guys. So if you have not done any of the homework, please start doing them. You can do them from the network. Get me as soon as you can. Them for now. So that's all I have. See you next week. Thank you guys for listening. The AMI one is not the quiz. You have to go to the site and download a couple of homeworks from there. Email Amy if you don't know how to go there. Quiz on their site, and you guys have access to it. You just load it, answer them, and email them to me. And right now I collect them. So drop, be able to set you up. Yeah, no better than it's the last, not the quiz. This came last minute, guys. So do them, and not into consideration. Just do your best. Thank you. Clear about explaining it. It came the last minute. They added it to us. All right.